Hello and welcome to another video of our GUNT HM250 fluid line series, Fundamentals of Fluid Mechanics. In today's video, we are going to show you the free discharge from a tank experiment. Let's take a quick look at the theory behind the experiment. And for this, we use an old friend, Bernoulli's equation. In this case, and with its variation and resulting simplification, it is also known as Torricelli's theorem. When comparing location 1 on top of the open tank and 2 right at the outlet of the nozzle, we can make a couple of assumptions. Firstly, the velocity on the surface is virtually zero, so we can get rid of this factor here. Secondly, we use our nozzle as the reference point, and therefore this factor here also becomes zero. And thirdly, the static pressure and density in either location are the same, so those factors on either side of the Bernoulli equation cancel out. What we are left with is this equation here, and it does look familiar because it also describes the velocity of an object which freely falls from the same height as our water level. Also interesting to note is that the diameter of the nozzle doesn't even appear in this formula. In other words, it does not have an influence on the discharge velocity. Or does it? That is exactly the point of having different nozzles in order to analyze whether the experimental data differ from the theoretical values. Let's do it. Let me show you the experiment unit. The internal pump of the HM250 base unit is speed controls in order to maintain a constant water level in the tank, which in turn is measured via the static pressure at the bottom. There are 4 nozzles to choose from with different diameters and shapes. The transparent experiment section has a grid, but we measure the trajectory parabola more accurately with this digital depth vernier caliper, which transfers the measurement data to the HMI of the HM250 base unit. In order to start the experiment, we simply select a set value for the water level, let's say 300 millimeter, and start the pump. We observe the water level going up, and by the way, this in itself could be an experiment in control engineering and liquid level control. As you can see here, the water level approaches the set point and after a slight overswing settles down on the set point. Once that is done, we can start our measurements by simply adjusting the digital depth vernier caliper in the respective location. As always, we record the data by pressing the plus button on the screen. Once we've done that for all locations, the result is this parabola here. After transferring the data in your preferred spreadsheet program, you can compare the measurements for the respective nozzles to the theoretical values. To summarize our experiment, we can say that the smaller the nozzle and the less rounded it is, the greater the deviation of the measurement value from the theoretical value. Now you could calculate the pressure loss coefficient of the respective nozzles, but for the sake of brevity of this video, we refer you to the instruction manual for the HM250. We hope you enjoyed this little experiment as much as we enjoyed conducting it for you. As always, for more information, please visit www.gunt.de. Thank you for watching, goodbye, and good luck with your teaching endeavors.